Making a truly successful product isn't just about how it looks or what it does, it's about choosing the right materials. The best design use materials not only perform well but also offer a great value and an experience that feels just right for the users. In engineering, materials are typically grouped into six broad families: metals, polymers, elastomers, ceramics, glasses, and hybrids, also known as composites, which blend two or more of the others. This classification isn't just for convenience. Each family shares the key traits like similar properties, manufacturing methods, and often even the type of application they are used in. The materials universe is like hierarchy. At the top, we have a broad families like metals. Within metals, there are a class called aluminum alloys. Dig deeper and you will find subclasses such as 6000 series, and within that a specific material, alloy 6061. Metals are known for their stiffness, something we measure using what's called a modulus of elasticity or elastic modulus. Pure metals are often soft and easily deformed, but through alloying, heat treatment, and mechanical processing, they can be made much stronger while still remaining ductile. That ductility allows them to shape through processes like rolling, forging, or extrusion. Metals are also tough with high fracture toughness, and they are excellent conductor of both heat and electricity. But they are not perfect. Most metals are reactive, and if left unprotected, they corrode quickly. Ceramics, on the other hand, are non-metallic and inorganic. Think porcelain or the alumina used in spark plug insulators. They offer a different set of strength. They are extremely hard, abrasion resistant, and maintain their strength even at high temperatures. Ceramic also resist corrosion and are excellent electrical insulators, but they are brittle. Their fracture toughness is low, which makes them sensitive to cracks, holes, or any sharp points of stress. Their brittleness makes ceramics harder to design with compared to metals. Then we have glasses, non-crystalline or amorphous solids. The most familiar are soda lime and borosilicate glass used in bottles and kitchenware. Because they lack crystalline structure, glass don't deform plastically. That's make them hard, highly corrosion resistant, and great electrical insulators. And of course, they are transparent. But like ceramics, their brittleness makes them vulnerable to cracking under stress. Polymers are organic solids made from long chain of carbon atoms and in some cases silicon. One of their standout feature is how lightweight they are. With densities lower than even the lightest metals, polymers are ideal when weight reduction matters. But here's the catch. Their properties changes with temperature. A polymer that feels tough and flexible at room temperature might become brittle in freezer or turn soft and rubbery in boiling water. What makes polymers so widely used is how easy they are to shape. That's why we often call them plastics. Complex parts, even those with multiple functions, can be molded in one go. And thanks to their flexibility and snap fit design potential, they make assembly fast, efficient, and cost effective. Elastomers, found in everything from rubber bands to running shoes, are a special class of polymers. What sets them apart is their incredibly low stiffness. Their modulus of elasticity is 500 to 5000 times lower than that of metals. But the real magic lies in their stretchability. Elastomers can be pulled too many times to their original length and still snap back to their original shape when released. It's this unique combination of flexibility and resilience that makes them so useful in everyday products. Hybrids are materials made by combining two or more different substances designed to bring out the best properties of each. Glass and carbon fiber reinforced polymers known as GFRP or CFRP are great examples. Interestingly, nature has been using hybrids all along. Materials like wood, bone, skin, and leaves are natural hybrids. Take bone for instance. It's a combination of collagen, a flexible polymer, and hydroxyapatite, a stiff mineral. Together, they create a material that's both strong and resilient. But choosing the right material is only half the story. The other half lies in how it's processed, how we shape it, join it, and finish it to bring the final product to the life. A process is simply the method we use to shape, join, or finish a material. From casting and injection molding to welding and electropolishing, there are hundreds of processes available. And choosing the right one early in the design stage is crucial. Waiting too long can make changes expensive and complicated. But here's the thing. Your choice of materials directly affects the processes you can use. Polymers, for example, can be molded. Brittle materials can't be forged like ductile ones. They need alternative methods. If a material melts into low viscosity fluid, it can be cast. If not, we have to take a different approach. Even the shape of the final product matters. Long, slender forms are perfect for rolling or drawing, but difficult to cast. Hollow parts, you can't force them, but you can mold or cast them. In the world of material science, every decision is connected. Forming processes are the foundation of manufacturing. The first row includes 6 primary methods: casting, molding, deformation processes like forging and rolling, powder based methods, composite forming, and special techniques like rapid prototyping or 3D printing. Once the basic shape is made, secondary processes come into play. This include matching to add detailed features and heat treatment which improves the surface or internal properties of the material. Together, these processes shape not just the form but the function and performance of the final product. So in the world of manufacturing, the process universe is divided into 3 main families: shaping, joining, and surface treatment. Let's start with shaping. This includes major process classes like casting, deformation, and molding. Take molding for example. It branches out into more specific methods like rotational molding, blow molding, and injection molding. Each of these has its own strengths and limitations depending on materials, the shape, and the required precision, and even ideal production batch size. Processing doesn't just shape materials, it can transform their properties. Take forging for example. Hammering a metal make it harder, but heat it afterward, a process called annealing, and it softens again. Even plastic shows this behavior. Polyethylene, the material in plastic bags, becomes 5 times stronger when stretched into fibers. And soft, flexible rubber, it becomes hard and brittle when vulcanized. When it comes to joining, there are 3 broad classes: adhesive, welding, and mechanical fastener. Each plays a critical role depending on materials involved in the performance needed from the final assembly. Joining also changes the material behavior. In welding, parts are melted and fused together, but the weld zone often ended up with different and usually worse properties than the rest of the material. Finally, we have surface treatment. This includes finishing processes like coating, polishing, or hardening that don't change the overall shape but enhance the surface. Finishing adds cost, so it must add value by protecting the surface, improving the durability, or simply enhancing the appearance. Surface treatments are generally used to enhance performance. Electroplating protects against corrosion, while processing like carburizing makes surface tougher or even wear resistance. In every case, processing isn't just about shape, It's about engineering the right properties exactly where they are needed. Materials and processes shape everything around us, from the things we use to the way they perform. Smart choices in both lead to better, stronger, and more efficient designs. So now you understand the basics of the manufacturing process. We will learn in detail in our future videos. With that, if you are curious about something, comment below or email us. Subscribe to Material Engineer to deep dive into the world of material science. Hit the bell icon so you can never miss an update. Until then, keep learning, keep asking, and keep exploring.